Okay, so welcome to the last section that we're going to be talking about in this class, section 6.2. Here we're going to be talking about volumes. So I'm going to start off with an apology with some of my drawings because I will be attempting to draw 3D shapes in this section. And I'm not 100% great with those. But let's get started. So what are some volumes we could think of some shapes that we know? From geometry, you could think of stuff like a cylinder with radius r and height h. You might think of a cube, or more generally, a rectangular prism, where you have the base has base and then width and then height. And you can think of, well, what's the volume of these things? From geometry, pi r squared h, and base times width times height. Okay, so now another thing we could do with these shapes is I could just take a slice of it. So like, if I take a slice of it, I get this circle, right? It's like I'm taking a knife and I'm cutting through this shape, and whatever I cut through, it's my new shape. And this is called a cross section, this type of action. So what is my cross section if I cut horizontally? Well, I'm going to get this two-dimensional shape, and its area is pi r squared, because I'll get a circle of radius r. What about this rectangular prism? Well, if I cut it horizontally, I'll get a rectangle whose area is base times width. So we could start to think of some questions like, how do these two things relate to each other? Cross-sectional area and volume. Well, notice that what it's looking like is V equals A times H. Now this goes back to the beginning of chapter 5. We talked a lot about the area problem, but also the distance problem. When we have two known things being multiplied together, that typically will translate into an integral. So for computing volume, it might help to somehow think about it in terms of an integral. And that's what we're building towards. So whenever we were doing the integral before and constructing the integral, we would have some graph. You would have your A, you would have your B. You'd have your rectangles. And they would have some little width, and then they would have some height, which was your function value. Now here, we still have our width, right? Our volume was area times height. This height is now our width, our delta x we have here. But what's this area? Well, this area is what we called our height before, our function value. So really, what we're doing here in this is this cross-sectional area. We can think of it as similar to how here we thought of it as the function value. We'll think of this area as a function. Which, if you think about just a general solid, like, it's doing all weird things, we can think about the cross-sectional area. At one point in time, it might be, say, a disk. At another point in time, maybe it's a smaller disk. And then over here, who knows, maybe it's some weird shape that's not quite a disk. So the area of that thing will be just continually changing. And when it's changing like that, thinking about it as a function may help. So this sort of approach does make sense. Okay, so let's come out with just a concrete thing to say what about this volume, and sort of summarize what we've said so far. So let's take a 3D shape or a solid. And it's going to lie between x equals a and x equals b. If the cross-sectional area, so that's the area we get whenever we make those slices of the solid, perpendicular to the x-axis, meaning, we're just taking horizontal slices, right? We're not taking like some sort of weird diagonal thing. If we call this a function, a of x, which we're going to want this thing to be continuous, then the volume, or we're going to call the volume of S, is, well, we're not going to just multiply a of x times b minus a. Similar to what I was saying before, we want to translate that into an integral. So, let's take this one. We can take partial sums of a xi star, so that's our sample point, delta x, or the integral from a to b, a of x dx. And that is basically what we're doing with this section, is talking about this integral. So let's look at a couple examples, and we won't look at the Riemann sum one. We'll look at this just as a definite integral. Okay, so let's look at this example. let y equal square root r squared minus x squared. So what does that look like? Well, that looks like this thing, where this is r and this is negative r. So what I'm going to say is I want to take this graph and rotate, because right now it's a 2D shape, rotate around the x-axis. So what happens? So basically, I'm taking this and I'm rotating it. So maybe it's over here somewhere later, and then down here at the bottom, and then behind. And I'm getting this new solid. Now, what is that solid? Well, this will actually give us a sphere. Because my drawing skills, it's sort of hard to looking at it, but especially because that is not quite center like how it should be. But it should be a sphere. So let's calculate the volume. We know what the volume of a sphere should be, so we'll check it against whatever we get using that integral. Okay, so let's look at the cross-sectional area. So if we want to do perpendicular to the x-axis, that gives us that slice, giving us, well, it's going to be a circle, right? And here will be where the x-axis is. It's like going through the board. And then if we go from the x-axis up to here, that's the same as going from that center up vertically to here. And what is that height? Well, that height is just y. And we can calculate that area. It's pi and then the radius squared, or y squared. Or pi r squared minus x squared. And that gives us our cross-sectional area. So we can calculate volume from that. It's the integral negative r to r area dx. Okay. So our volume is pi negative r to r dx minus pi negative r to r x squared dx, or pi x from negative r to r minus pi over 3x cubed negative r to r. This is going to be r pi minus pi times negative r, and then all that minus pi r cubed over 3 minus negative pi r cubed over 3. And from here, we're just simplifying this thing. So this is going to be 2 pi r minus, in that parentheses, we'll get 2/3, r cubed. Sorry, there should be an r squared there. My apologies. 2/3 pi r cubed equals 4/3 pi r cubed. So it does agree that the volume of this shape is the same as the sphere, like we would expect it to be, which is 4/3 pi r cubed. Now let's go back to how we computed that thing. What was the steps? Step 1, find the cross-sectional area, which, when you revolve around this x-axis, that cross-sectional area was just pi, and then whatever your y value is, squared. As it turns out, if we're going to do this method of revolving around the x-axis, it's going to be something that looks similar to that, or even just revolving around any line will look similar to that. Then what? We compute this integral. And then we're done. Now there's a lot in those two steps, but those are the two steps for finding volume. Or we'll call this volumes of revolution oftentimes. Okay, so let's do another example. One that's not a common shape. Let's take this function y equals 1 over x, and then x equals 1, x equals 6 as our bounds. Then we could look at this area bounded by those conditions and revolve it around the x-axis. So what is the volume? Well, from before we said our area is pi, and then our function on top is 1 over x squared, or pi over x squared. So we can integrate that to get our volume is from 1 to 6 pi over x squared dx, or pi, well, we use the power rule for anti-differentiation. You add 1 and you divide by the new power, evaluated from 1 to 6, negative pi over 6 minus negative pi over 1, or pi minus pi over 6, or 5 pi over 6. So the area of revolving that shape is going to be 5 pi over 6. And then we're done. Now, as a last example for today, you can get something that, what if we want to not revolve it around the x-axis and do something similar to last section where we just took everything and wanted to do everything with respect to the y-axis. An example is x equals y squared, y equals 0, y equals 1, revolve around the y-axis. So what does that look like? Well, you have a parabola on its side. You have this area. And we want to revolve it around the y-axis. Okay. We can still do this. But now instead of pi y squared, it's not pi y squared, because now our function is reverse. It's pi x squared. So whatever axis you're revolving it around, this is going to be the other variable. And we could see that if we do a cross section, this is revolving around, and then we'll get, our slices will be something looking like this, where that radius is now our x coordinate. So what does that give us? Well, that's pi x, or y to the fourth. So we can integrate that from 0 to 1, pi y to the fourth dy, or pi over 5 y to the fifth from 0 to 1, which is pi over 5. So you can also do it with respect to the y-axis, not just the x-axis. Okay, so that is what I have for today. Tomorrow we will continue talking about this, and in fact talking about something else called so this was the disk method, because we were making disks. Tomorrow we'll talk about the washer method, where it's just a little slightly different.